which element of the chlorine has the least amount of second ionization energy? Least amount of. So to answer this question, we have to draw the first ionization energy graph first. Hydrogen, helium. I start from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Then remember that the first ionization energy of oxygen and the ionization energy of hydrogen are almost same. Actually, it is same value. So this is oxygen starting from lithium, then nitrogen, oxygen, and here neon. Then the ionization energy of hydrogen is here. Then helium as the highest. So you will get this kind of a graph if you connect all these points like this. Lithium. We call that characteristic zigzag variation. Then again, when we consider from sodium onwards, the sodium will have ionization energy than lithium. So sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. So we can connect these lines also. Then the graph will be like this. Then the second ionization energy normally we draw starting from the second group and follow the same variation, same pattern. Like this. And then here. Like that. So this is the blue color, the second ionization energy graph. Then we have sodium, magnesium, aluminium, and silicon. So silicon, the second ionization energy of silicon here. The sodium here. Chlorine, oh, the chlorine is then oxygen, chlorine here. The lithium may be somewhere here. Like this. So lithium, then helium, maybe here. Like this. The second ionization energy of any element is greater than the first ionization energy of the same element. Therefore, we can now clearly see that the silicon has the least. Lithium here, helium here, and fluorine here, then sodium here. So silicon has the least first ionization energy. So your answer must be the medium. The second question. Which statement from chlorine is correct about the quantum numbers? Azimuthal quantum number expresses the orbital in which the electron belongs to. Azimuthal quantum number, we have Normally we have 4 quantum numbers. N represents the main energy level, though we call it the principal energy level. N can take 1, 2, 3, 4 up to infinity. The azimuthal quantum number, or sometimes we call the angular momentum quantum number, denoted by simple L, it represents the sub-energy levels. So L can take minus 0, 1, 2, 3 up to n minus 1. L equals 0 represents the S sub-energy level, L equal 1 represents the P sub-energy level, L equal 2 represents the D sub-energy level, and 3 for F sub-energy level. Then we have another quantum number called the magnetic quantum number. This gives us the atomic orbitals. Normally we know that S orbital is spherical, P orbitals are dumbbell in shape. Then for P sub-energy level, we have 3 identical atomic orbitals. Identical means their energy same, size same, shape same. These are S orbital, spherical, P orbitals, dumbbell in shape, and those are oriented in 3-dimensional space like this. This is x-axis, this is y-axis, and this is the z-axis. Then this may be the PZ, this is PX, and this is PY. Those are named according to the coordination axis in 3 dimension. Then for ML values, if L equals 0, that means M0. If L equals 0, the ML value is 0 only. If L equals 1, then ML can take -1, 0, and +1. That means this may be, say, PX, PY, and PZ, say, because we have actually the correct numbering system, but in our level, we don't consider that. So therefore, I can randomly name them as PX, PY, and PZ. Right? So this ML will give us the atomic orbitals like this PX, PY, and PZ. For L equals 2, we have ML values -2, -1, 0, +1, and +2. That means for d orbitals, we know that this represents the d orbitals. For d sub-energy level will be represented by the L equal to, so L equal to has 5 ML values, means d orbital or d sub-energy level has 5 d orbitals. Yeah, 5 d orbitals. Okay, so our question now says the azimuthal quantum number expresses the orbital in which the electron belongs to. Azimuthal quantum number gives a sub-energy level, not the orbital. Orbital is given by the ML. See here, orbitals are given by ML. Here for P sub-energy level, we have 3 orbitals. Px, Py, and Pz, like that. For the d also we have dxy, dyz, like that. Ds squared minus y squared, like that we have 5. Okay, so here we have 1. Therefore, first one is wrong because the azimuthal quantum number represents the subenergy level, not the atomic orbit. Second one, during the movement of electron in an atom, the principal quantum number changes always. Never. Normally, during the movement of electrons in an atom, the principal quantum number changes always. Normally, we know that electrons are moving around the nucleus in definite energy level. If energy gives to that electron, it will transfer from low energy to high energy level, or if it is in a high energy level, then it will come back to low energy levels by releasing energy. So it will not always changing, but sometimes it will change when energy absorbed or release. If absorbed, the low energy electron will move to the high energy levels. If it releases, then it will come back to low energy levels by releasing some amount of energy. For this, actually, it absorbs energy and from low energy levels to high level. So, the second one is wrong. That means during the movement of electrons in an atom, movement may be orbiting around the nucleus, or sometimes movement may be from or in between two energy levels. If it is moving in between two energy levels, it changes the quantum number. Otherwise, it will be same. We know that if electron moves in a sub-energy level, it has a quantum number. Say ml equals 0, it is. And if it is moving in clockwise or anti-clockwise direction, there's another value called that ms or s value. That is a spin quantum number. Plus half or minus half. Sometimes this may be interchange, but they have some definite value. If an electron has minus half, it has always minus half. It doesn't change. Therefore, during the movement of electron, the principal quantum number will not change. Principal quantum number will be changed only when the electrons are transferred from one energy level to another. Third one, the orientation of orbital is expressed by the magnetic quantum number. Yeah, that is ml. Orientation. Orientation. The orientation of the orbital is expressed by the magnetic quantum number. Yes, Px, Py, or Pz will be given by this ml value. ml value is known as the magnetic quantum number. So that is correct. The third one is correct. These are wrong. The fourth one, an energy level with a principal quantum number of n, the maximum number of electrons it can have is n squared. Yes, that's, see, maximum number of electrons. Here n squared actually will give us the number of atomic orbitals, like this way. If n equals 1, n square equals 1. N equals 1 means first energy level, it has only one orbital, that is 1s. If n equals 2, second energy level, it has L values 0 and 1. 0 means a sub-energy level, 1 is the P sub-energy level. So, S has only one atomic orbital and P has 3. P has Px, Py and P is 3. Then altogether 3 P's and 1 S. So altogether 4. N squared equals 2 squared equals 4. Then atomic orbitals, number of atomic orbitals will be given by N squared. And we know that in each atomic orbital, there can be maximum of 2 electrons. So if you multiply this by 2, then only you get the number of electrons in a given sub-energy level. It is, sorry, given main energy level. It is N squared. The number of energy, the atomic orbitals N squared, the number of electrons will be 2 times N squared. Right? So we know that in S orbital we have 2 electrons, in P we have 6. Then altogether 8. 8 is equal to 2N squared. So 2 times N squared will be the number of electrons in a given main energy level or principal energy level. Therefore, this is wrong. This is not the maximum number of electrons. That is the maximum number of atomic orbitals. So therefore, this is wrong. Fourth one is wrong. The building up of electron in the ascending order of the principal quantum number will always minimize the energy of them level. Why? The building up of electron in the ascending order of the principal quantum number will always minimize the energy of them. Let's see. According to that statement, first it will fill the electron to first energy level, N equal 1, then N equal 2, then N equal 3. That means 1s, then 2s and 2p, then 3s, 3p, 3d. If N equals 4, then 4s, 4p, 4, 5, and 4p, 4d, and 4f. This is the thing it says. But we know that electrons fills according to Auber rule. It is 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So electron will fill first 1s, then 2s, then 2p, 3s, then 3p, 4s, 3d, 4p, and 5s, and so on. That means before completely fill the third energy level, the electron fills to the fourth level. After 3p, it fills to 4s, not the 3d. If all the 3d atomic orbital fills and then electron fill to 4s, that is the statement says. According to the statement, electron must fill to first energy level, then the second, then the third, then the fourth, and so on. But we know that before 3d, electron fill to these 4s. Therefore, that statement is also incorrect or wrong. So your correct answer is then third one.